Hello everyone and very warm welcome to our DIY 2 project presentation. We are group number 9 presenting a department EXTC and CC at KJ Somaya School of Engineering College. So today we are going to explore a fantastic highly practical algorithm framework, parameterized algorithm approximation of TSP non-metric graph. Essentially we are looking at how to bridge between perfect, exact mathematical and mess chaotic reality of real-world logistics. This presentation anchored at 2025 research paper by Zhao, Zhang and Zhou. My name is Gaurav Singh and I'm joining by my teammate Utkarsh Pandey and Parth Chheda. We would like to thank our guide Professor Rupali Patil ma'am for her continuous support, and let's dive in. To understand this breakthrough, we have to start a foundation challenge in computer science, the traveling salesperson problem, a classic definition of simple state, and find absolute cycle for this cycle, to visit every vertex exact once and return to a start. Historically, most of the algorithms assume a matrix TSP is matrix space distance obey a triangle inequality, which mathematical way of saying a direct straight line from point A to point C, in which way a shortest path. However, our focus is today on non-metric reality in non-metric graph of fundamental rules of geometrical fields. You might be wondering, why does this matter? Why would a triangle inequality ever fails? Because in real world chaos, urban transport network defect and mathematical glitch. Imagine driving in Mumbai, going back to point A to point B might take 10 minutes, but going back to point B to point A could be take 45 minutes because of one-way streets. We have traffic congestions and various times interaction and geopolitical borders. When a time apply and non-approximation algorithm, our NST based approach to a real world non-metric graph is fundamentally breakdown. They abstract a bad logical roots because they blindly assume the triangle inversely exists. So if a standard approach ever fails, how to get a guaranteed correct answer? So we are exact dynamic problem, specifically Hellcraft algorithm. A Hellcraft algorithm is a state where define a calculated minimum cost to visit a set matrix. It is use a recursion break a massive routing problems down into smaller overlapping problems of subproblems, building up from a best case to zero a final optimal answers. It's mathematically perfect and it is fertile loss. So exponential bottleneck is a time complexity of Hellneck big O of n square of 2 times power n. So means it's a delivered network hit about 25 location computation become a practically impossible of a standard computer systems. We need to fast the way. The explanation we will solve by diagonal entrances by presenting our main approximation algorithm. I will hand the presentation over Utkarsh Pandey.
Thank you, Gaurav. So we face a massive dilemma. We want the speed of polynomial time algorithm so that we can scale up to thousands of cities. But we also need accuracy, a bounded guarantee relative, to optimal route. The traditional trade-off is that you sacrifice a little bit of accuracy to gain massive amount of speed. But as Gaurav explained, without triangle inequity, those traditional methods fail entirely. This is where the authors introduce a new method known as parameterized complexity. Instead treating of the whole graph as chaotic, they introduced a parameter which is known as k that represents the specific degree of non-metricity. Let me explain how powerful this is. The first step is non-metric edge isolation. Imagine a massive logistic network of 1000 roads. Usually, a small fraction of those roads, let's say 20 of them, actually violate metric rules due to extreme traffic or terrain. We identify those specific problematic edges as k. By isolating the chaos, we achieve fixed parameter trackability (FPT). This is a core breakthrough. The algorithm's heavy exponential complexity is now strictly limited to the small parameter k, while the main network n remains comfortably polynomial. This allows us aggressively to prune the state space. If algorithm sees a path that is clearly terrible, it eliminates it immediately using k as the bound and saving massive amount of the memory. The algorithm execute this logic through a clean three-phase pipeline. Phase 1. It is a non-metric mapping. Before calculating any routes, the system scans the graph, pre-processes it, and separates and predictable metric substructures from K non-metric violation. Phase 2 is a state space truncation. This is where heavier lifter works. The algorithm applies parameterized pruning and purging bad state from the memory early on so the computer does not crash due to data overload. Finally, phase 3 is a subroute assembly. The system takes the surviving optimized partial routes and stitches them together using dynamic programming. Retention those the non-metric edges with straight error guarantees. But how accurate is this practically? For the mathematical proof and the real world result, I will pass it to the Parth.
Thank you, Utkarsh. When we talk about algorithms at this level, we can't just say it's fast. We have to prove it mathematically. The authors established a strict approximation bound. The algorithm guarantees that the calculated tour will be less than or equal to 1 plus epsilon times the absolute optimal tour. This means we can manually control the quality of our route by adjusting epsilon. Furthermore, look at the time complexity. It is big O of 2 raised to k into n cube divided by epsilon. Because k, the number of bad edges, is usually very small in the real world, this formula is effectively polynomial in n. The proof technique relies on a charging argument mapping the algorithm solution back to the optimal tour while strictly bounding those k non-metric contributions. But theoretical math only matters if it works in practice. The authors evaluated this algorithm on simulated real-world asymmetric graphs, ranging from 50 to 200 vertices with 5 to 15 non-metric edges. The empirical results are incredibly decisive. The parameterized FPT algorithm we have presented achieved 95% efficiency rating compared to the absolute optimal. For context, the industry standard genetic algorithm only achieved 78%, while greedy nearest neighbor approach dropped down to decimal 60%. This proves definitively that we no longer have to choose between exact solvers that take years to compute and fast heuristics that give terrible routes. So, where does this leave us in the real world? The applications are highly lucrative. First, global supply chains. Shipping companies can now easily calculate asymmetric maritime routes, factoring in directional wind patterns, port fees, and border constraints. Second, 3D drone delivery. Drones fight gravity, wind, and battery discharge rates. A drone flying against the wind is the ultimate non-metric edge, and this algorithm thrives in that airspace. Third, disaster relief. When earthquakes destroy infrastructure, standard metric maps fail. This framework calculates emergency routing instantly around the chaos. Looking briefly at the future scope, the potential of this research is vast. The logical next step is integrating this parameterized approach into complex vehicle routing problems or VRPs where multiple fleets of trucks are deployed. Eventually, we foresee this powering AI driven, self learning logistics networks that can instantly recalculate routes when dynamic edge failures, like a sudden bridge collapse, occur in a real time. To bring it all together, let's look at the conclusion of this 2025 paper. For decades, computer science has been trapped in a rigid trade off. By isolating the chaotic non-metric edges into a single parameter k, Zhao, Sheng, and Xiao achieved three things. First, the bridge. They successfully united exact dynamic programming and modern approximation theory. Second, the solution. The parameter k completely neutralizes the NP-hard exponential bottleneck that has plagued the held carp algorithm for years. And finally, the verdict. This provides a highly scalable, practically bounded solution for real-world non-metric logistics. On behalf of Gaurav, Utkarsh and myself, we would like to once again thank Professor Rupali Patil for her guidance on this IA2 project. Thank you all for your time and attention. Thank you.